Hello, this is Math 2270 coming to you from the College of DuPage during the summer of 2020, and this is the first continuation of the lecture entitled Introduction to the Laplace Transform. When last we left off, you were computing the Laplace transform of e to the at, where a is a constant, and I hope you finished this, but just in case you didn't, here's another chance. You know what to do. Let's see how you did. So here we're using the definition of the Laplace transform for e to the at. And now we're using properties of exponents where we add those exponents and we factor out the t. So this is e to the, and this is a constant as far as the integral is concerned, because the integral is with respect to dt. So this was playing the role of the c on an earlier problem that we did. So if we let c equal a minus s, as we did earlier, we recall that this was minus 1 over c. And that was provided that c, the role that's being played by a minus s, was less than 0. So we can take this minus sign, shove it into the denominator, and we change the order of those. And so you see that the Laplace transform of e to the at is 1 over s minus a, provided s is bigger than a. Let's do another one. Here you are to compute the Laplace transform of the sine of at, where a is a constant. You know what to do. Let's see how you did. So that's going to be a function of s, and here's the definition of the Laplace transform of sine of at. And this is going to be the limit as n goes to infinity of the integral from 0 to n of e to the minus st sine of at dt. Now let's continue working up here, because we're going to leave the limit out here and we're going to integrate this. But this is an integration by parts. And so we do the integration by parts. This is going to be uv minus the integral of v du. And there's a lot of constants to deal with and things like that. And we're going to substitute n into here first, and then minus 0 into here. When you substitute 0, the cosine of 0 is 1, and e to the 0 is also 1, so you're going to get minus 1 over a. And so that's where the 1 over a comes from here. And when you substitute the n in, this is what you get, minus. Now this one, you have to integrate by parts again. And so when we integrate by parts again, the minus s over a stays out here, but you get uv minus v du, the integral of v du. And so we evaluate this, and when we put 0 in here, the sine of 0 is 0, so that's going to drop out and we get the sine of n. So when we're looking at this, then we will get f of s is equal to that expression minus this expression. That's where I substitute those values in, and then it is plus this expression. Now what happens then is we observe that as n goes to infinity, this is going to go 0, because you have assuming that s is bigger than 0. So what you have is that is a negative exponential times a cosine that's going to go to 0 by L'Hopital's rule. And similarly, this one is going to go to 0. So this simplifies a great deal, and this is what you have, 1 over a minus s over a, and this is s over a again, and this integral. But this integral here, we're going to realize is s over a times, that is the Laplace transform again of the sine of at. But let's not get ahead of ourselves. So here we do some more arithmetic, and we use the fact that those were going to 0. So now we go over it this way, and we realize that this is f of s is equal to 1 over a. This is s squared over a squared. But this thing is, again, f of s. And this is a harbinger of the way that we're going to do this, because now we have to use algebra to solve for f of s. And you should do this step yourself. But if we solve for f of s here, what we'll get is that f of s is equal to a over s squared plus a squared, provided s was bigger than 0, and we needed that, so we had convergence up here. So you see we have computed this again, so that's good work. But it was a lot of work, and we're really about solving differential equations, not just computing integrals. And so we're going to look ahead to how we're going to be doing it. We're going to be using tables. And tables, this table has a column that is called f of t. And so that is lowercase f of t. So this is the function. And then we have a capital F of s that is going to be the transform. And we've done 3 examples so far. So for example, we took and found the Laplace transform of 1 was 1 over s. We found the Laplace transform of e to the at was 1 over s minus a. We also found that the Laplace transform of the sine of at was a over s squared plus a squared. So we have a table of these, and we're going to be using them not only for the Laplace transform going this way, but for the inverse Laplace transform going the other way. It's a very important table, and you will have this in the grace notes on your final exam. And you notice that the gamma function appears, and many things appear in this in this table. Let's give the table a ride in just a moment, and but we are going to not only use the table, but we're going to use the linearity. So if I take the Laplace transform of a f of t plus b g of t, it's going to be a f capital F of s plus b capital F of g for any constants. So you use this to compute more complicated things. So now let's look at an example then. There's 1, 2, 3, 4 examples here. I want you to find the Laplace transforms of the given functions for this. I am putting that table in your syllabus tab for you to use, and this is the one that we will use on exams. You know what to do. And we'll see how you do in 25.2.